Hello friends, I welcome you to the last lesson of electric fields. IBM is my name and this is going to be the last lesson of electric fields. Don't forget to subscribe and always follow the lessons. I'm going to attach a copy of the past paper questions because after completing lesson 4, the next episodes of electric fields will be actually solving past paper questions so that we gain confidence in solving or handling these questions in exams. The document which has past paper questions will be attached at the end of the video, and you can always, it is attached in the description. You can click on the link. When you click on the link, I'll receive a message to allow you to download, or I give you permission to download the document so that you can always have it in the best thing is to have it in hard copy so you can print it. And if you are following the video, if the document is printed, you can easily follow through the document as you follow the video. That's how you're going to learn and gain confidence in dealing with electric fields. Remember, there are two parts of electric fields. The first part was a uniform electric field, and the second part is now the field due to a point charge. And I mentioned in one of the videos that electric field due to a uniform field was actually AS in the past, but now it has been combined. So we study it as electric fields in A level, paper 4. So let us start, and today we shall look at the last part, which is electric field potential and electric potential energy. Okay, so the last time we were here, I think we were dealing with, we stopped on the self-check, and I hope you tried to solve the self-check and you didn't find much challenges about this self-check. You can always inbox me, you can always write to me about the self-check. You can always ask your questions about the self-check. I can always help you to solve or to understand some of those questions. So let's move directly to electric potential, which we are going to represent with the letter V, as opposed to as opposed to gravitational potential, which we represented with the letter phi. Before we introduce electric potential, I want to remind you of gravitational concepts, where we talked about gravitational potential, the work done in moving a unit mass from infinity to a point in the gravitational field was given by phi equals negative g capital M over r squared, where we say that for gravitation, the negative was not optional, and we explained or gave an explanation as to why the negative is compulsory. If you recall, we said potential at infinity was defined to be zero, and the force between two masses was always attractive. And if potential at infinity is defined to be zero and the force between two masses is always attractive, it means when you move a mass from infinity closer to another mass, you are moving it in the same direction as the field. So work is got out of the mass. If work is got out of the mass, or energy is got out of the mass, it means the energy decreases. And if energy decreases or potential decreases, it means the potential is going to be less than zero, therefore it will be negative. So you must have that in mind. And we said, if now we consider moving the whole mass from infinity, not just a unit mass, we therefore have what we call potential energy. Potential energy at that point was potential times the unit times the testing mass. This gave us potential energy as negative G capital Gm small m over r, and this was the expression for potential energy. So let's now think of moving a charge uh, from infinity to a point in an electric field. So note that when a body is moved from infinity, or when a body is moved in the field, there is always work done. It only depends on which direction the body is moving. Is it moving the same direction as the field, or it's moving in the opposite direction to the field? So if it is moved in the same direction as the field. Then the field does the work. That means work is got out of the object. If it is moving in the opposite direction to the field, that is the otherwise part, then work is added to the object, so the energy is actually going to increase, as we saw with the gravitation. In moving a unit mass from infinity to a point close to the earth, we normally say potential energy decreases. Actually, we say potential energy decreases because work is normally got out of the object. In moving an object from infinity to a point in a gravitational field, you are moving it in the same direction as the gravitational field. But think of a situation when we are moving a mass from the Earth's surface towards infinity. Normally, we say gravitational potential energy increases as the object moves away from the Earth's surface. The reason is because moving away from the Earth's surface, we are doing work against the field, which is towards the Earth. So we are adding energy to the object. That's why we say the gravitational potential energy increases for an object if work is done or if the object is moved against the field. So since we are dealing with electric potential rather than gravitational potential, we shall ignore the concept of masses and now concentrate on the concept of charge. The work done in moving a unit positive charge. This part is very important. Remember we said to define electric field strength, we always imagined a unit positive charge. So the work we are doing in moving a unit positive charge from infinity to a point in an electric field or against the electrostatic force is what we are going to call the electric potential. In a similar way, since we defined potential due to masses to be negative capital G m over r, in a similar way, the work done in moving a unit positive charge from infinity to a point in the electric field is going to be called um, electric potential. So it will also be given by a similar expression. Of course, deriving this expression will not be part of this lesson. However, the math students could derive this expression by integration. The work done in moving a unit positive charge from infinity to a point in an electric field is going to be given by this expression here. Of course, if we compare with the expression for gravitation, we would have V equals to KQ over R. Remember K, earlier on we have seen K is 1 over 4 pi epsilon naught. And 1 over 4 pi epsilon naught is approximately 8.99 times 10 power 9, as we have already seen. So these expressions are almost the same. Unfortunately, although we had a negative for gravitational potential, we don't have it here because electric potential will depend on the sign of the charge creating the field. Since we have both positive and negative charges, it means electric potential can be positive or it can be negative. Unlike a gravitational potential which was only negative, electric potential can be positive or negative because you can have a positive charge or a negative charge. So electric potential can be positive if the charge creating the field is positive, or it can be negative if the charge creating the field is negative. Okay, so I think you and me know that potential is a property of a point in a field, and therefore we are also talking about work being done, and the work is a scalar quantity. So it doesn't make any difference for us to say that potential is a property of a point in a field, and therefore it is a scalar quantity. So that means the idea of direction will not work here. Because we are dealing with the work done in moving a unit positive charge from infinity to a point. So potential and potential energy in general will also be scalar quantities, as we also saw in gravitation. Potential, we have already heard of potential in AS. We have heard of potential difference. Therefore, the units of potential will still remain the same, and that will be in volts. Now, we have considered moving a unit positive charge from infinity to a point in an electric field. Suppose now we take the whole charge instead of a unit charge. Instead of taking a charge of one coulomb, positive one coulomb from infinity, suppose we take the whole charge, maybe it is 20 coulombs, and we are to move 20 coulombs from infinity until we reach a point where the distance between the charge and the point is r. We are to move this charge of 20 coulombs to a point P. What is the work done? So it means if moving one coulomb from infinity to a point P takes the work done is called electric potential. So that means since we have a total charge 20 coulombs, or I'm calling it smaller q, then the total work done to move the whole charge from infinity to a point P, which is in an electric field, is going to be the product of this charge times the potential. The total work done is going to be the product times the change in potential. So the total work done is going to be the charge which we are moving from infinity times the potential, which is going to be actually a capital Q small q over 4 pi epsilon naught r. We are assuming the charges are in a vacuum. So the work done to move the whole mass, the whole charge q from infinity to a point in an electric field is now going to be called electric potential energy. So electric potential is work done per unit positive charge, moving it from infinity to a point in an electric field. And electric potential energy is going to be the work done in moving the total charge or the whole charge from infinity to a point in an electric field. So in summary, this is what I'm saying. The work done in moving the charge Q from infinity or from a point at infinity to the point in an electric field is going to be called electric potential energy. Sometimes you can still represent it with E subscript P, or you can say electric potential energy in calculation to be equal to Q times V. But I've said since V is equal to this, the electric potential energy is going to be Q capital Q over 4 pi epsilon naught R. Note that the sign of the potential can be positive or negative depending on the charge or the sign of the charge creating the field. So at this point, we shall either be using this for potential, or we shall be using this expression for potential energy. If we move from one point A to another point B, where point A and point B are at the same potential, it means the change in potential is going to be zero. Therefore, there will be no work done, because work done in this case will be equal to the charge we are moving from one point or point A to point B times the change in electric potential. Let's see some examples then. Example number one. The examples are straightforward and they are very easy, so we can just run through them. Let me pick my calculator so that this moves very smoothly. Okay, find the potential at point P, which is 10 centimeters from positive 10 microcoulomb charge. I can't press my calculator. So in our solution, set number one, maybe just for since we are starting, I can give you some of us learn by seeing pictures. Maybe I can try to put this in a picture. There is a large charge creating the field here, which charge I'm calling positive 10 microcoulombs. And we want the potential at a point P, which point is at a distance of 10 centimeters from this large charge. And this charge is positive. And I said the sign or the polarity of the potential is going to depend on the sign of the charge. If the charge is positive, creating the field, then the potential at the given point due to that particular charge is going to also be positive. Remember, electric potential V is given by charge divided by 4 pi epsilon naught R. And remember, 1 over 4 pi epsilon naught is the same as 8.99 times 10 power 9. Or if you don't want to use that, you could also use epsilon naught being equal to 8.85 times 10 power negative 12. This quantity is given, but I'm sure this one is not given. So whichever is easier for you, you can always use it. So the potential at point P, I'll call it potential at P, would be the charge creating the field that is positive. So we substitute, I'm just substituting this expression. So I'll say where there is 1 over 4 pi epsilon naught, I'll simply put this. So this will be 8.99 times 10 power 9, then times the charge creating the field, which is 10 times 10 power negative 6, divided by the distance r, which is 0.1. People would forget and square this, but that's not necessary for potential. That is not necessary. That's not necessary for potential. And if you press your calculator, you're going to realize that this gives you, I'm pressing my calculator. So this is giving me positive 8.99 times 10 power 5. The units are volts. For those who will want to square the denominator, I want to show you something before I proceed to examples number 2 and number 3. What do I want to show? This is just a by the way for those doing mathematics. So we have already seen that electric field strength due to a point charge is equal to Q over 4 pi epsilon naught times R squared. That was electric field strength due to a charge. Or we can just write this as KQ over R squared. It is the electric field strength which is squared. We have also seen that potential is equal to K. I'll just call it KQ over R. So when you combine these two expressions, you realize that E can be the same as the potential divided by R. But if you're a mathematician and differentiate, I'm going to try and differentiate V with respect to R so that I have dV by dr. dV by dr, note that this one is the same as KQ R power negative 1. So when I differentiate, KQ is a constant. The negative 1 comes in front, so it will be negative 1 times KQ R power negative 1 minus 1. That is how we differentiate for those doing math. So it means dV by dr is going to be negative KQ, but this is R power negative 2. So it means dV by dr is going to be negative KQ over R squared. When this one goes into the denominator, the power becomes constant. And realize that this one was electric field strength. So it means when I take this negative across and I replace this with E, it means E is equal to negative of dV by dr. This quantity here, dV by dr, we call it potential gradient. If you recall, in one of the lessons, I mentioned that electric field strength is equal to the negative potential gradient. That is the relationship between E and potential. Electric field strength is equal to the negative potential gradient. Electric field strength is equal to the negative potential gradient. Many times they will ask you to state the relationship between E and potential, and I'm saying the relationship is electric field strength is equal to the negative potential gradient. So I brought this so that you can always compare this and this so that you know the difference between E due to a point charge and potential due to a point charge. Okay. Number two, I will just erase because I don't have another space. Erasing this, number two, find potential X, which is 20 centimeters from a negative 5 microcoulomb charge at A. So the charge creating the field is negative. I know potential will be negative. So in our question number two, potential at point X is going to be K times Q over R, where K is 8.99. K is 8.99 times 10 power 9. We multiply this by the charge creating the field. The charge is negative 5 times 10 power negative 6. Divide by the distance, which is 0.2. That gives us the potential at point X. Press the calculator. So pressing the calculator is giving me negative 2.25 times 10 power 5 volts. Negative 2.25 times 10 power 5 volts. Then our question number three. I think question number three may require a lot of space, so I will have to wrap clear of this. So for question two, we have seen potential at X is a negative because the charge creating the field is a negative. Question number three. So question number three, find the potential at point B. Note that the signs of the charge will not be used for predicting direction as we did with electric field strength and the force. The signs of the charge will dictate that the potential is either positive or it is negative. Okay, so if I want the potential at B due to charge A, because charge A is negative, the potential caused by charge A is negative. Then the potential caused by charge C is going to be positive because the charge is positive. So it means the potential at B is going to be the total potential, which is the sum of the two values of potential. Potential will either be negative or positive depending on which charge contributes much to the potential. Therefore, the total potential at point B will be the potential due to charge A plus the potential due to charge C. So I'm substituting. Remember, potential is equal to KQ over R, where K is 8.99 times 10 power 9, or 1 over 4 pi epsilon naught. K is 1 over 4 pi epsilon naught. So potential at point B is going to be potential due to A, which is going to be K, that is 8.99 times 10 power 9. Then times the charge, which is, this is going to be negative 5 times 10 power negative 6, divided by the distance from B, which is 0.1, plus potential due to C, which is 8.99 times 10 power 9, times the charge, which is positive 10 times 10 power negative 6, divided by 0.05. So this is the total potential. Now you notice that it is only in potential where I'm including the positive and negative signs in calculation. Simply because potential is a scalar quantity, we cannot use the signs to predict direction. It is not necessary. So I'm pressing the calculator. So this is giving me negative 4.5 times 10 power 5 volts plus this is giving me 1.8 times 10 power 6 volts. So the total potential is the sum of these two. So the total potential is 1.35 times 10 power 6 volts. So that is the total potential at point B. Example number 4. Example number 4. Three-point charges Q1 and Q2 and Q3 of magnitude +5, +6, -20 microcoulombs are stretched along a straight line as shown in the figure above. Calculate the electric field intensity midway between Q1 and Q2. So we want E. This time we want E. It is good we are going to find E and potential at the same time, so we compare. If I want E is a vector quantity, the signs will help me to tell the direction of E. So this is +5 microcoulombs, this is +6 microcoulombs, and this is -20 microcoulombs. So I want you to realize that E, to define electric field strength, we imagine a positive charge here, +1 coulomb here. Q1 repels it to the right, so this will be E1 maybe due to Q1. Q2 repels it to the left, so this would be maybe E2. And of course this one, okay, that would be E2 will be to the left. Q3 is negative, it tends to attract our positive charge, so Q3, E3 is going to be in that direction. So the sum of these three is going to be, the algebraic sum of these three is going to be the resultant electric field strength at point C, I mean at the midpoint. So to be very clear, I will first of all find E1, because remember E is KQ, this is now R squared. So E1 will be 8.99 times 10 power 9. Then times the charge, which is 5 times 10 power -6, divide by 0.05 because it is midway. So we divide 10 by 2. You notice that here I have to square because it's electric field strength. So this gives me E1, or electric field strength caused by charge Q1. Press my calculator. Okay, so this is giving me 1.8 times 10 power 7 newtons per coulomb. Then E2, of course this is to the right. Then E2 is going to be similarly 8.99 times 10 power 9. Then times the charge is 6 times 10 power -6. Divide by 0.05 squared, that is the distance between the midpoint and Q2. I press my calculator. And this is giving me 2.16 times 10 power 7 newtons per coulomb. This E is to the left. I find E3, similar, it will be 8.99 times 10 power 9 times 20 times 10 power -6, divide by the distance between Q3 from the midpoint is 10 centimeters plus 5, which is 0.15, and this is also squared. So this is giving me 7.99 times 10 power 6 newtons per coulomb. So all we need is the resultant. This one was to the right because it was attracting our unit positive charge. Note that to come up with a direction, I imagine a unit positive charge at the midpoint between Q1 and Q2. So the resultant of all these values is going to be the resultant electric field. So when I add these, you can even give them signs and say, okay, those to the right will be positive, those to the left will be negative, so that when I add 1.8 times 10 power 7 plus 7.99 times 10 power 6 minus 2.16 times 10 power 7. And when you press your calculator, pressing the calculator is giving me 4.4 times 10 power 6 newtons per coulomb. And this is going to be to the right. In other words, the resultant electric field, the field to the right is greater than the field to the left. So if we put a unit positive charge here, it is most likely going to move to the right. E is a vector quantity. E is a vector quantity. Then part 2, potential. Potential midway between Q1 and Q2. Potential is very easy. You just sum up the potentials due to each of those charges because potential is a scalar quantity. So to use the same space, I'll first erase this. So potential at the midpoint is going to be potential due to charge A plus potential due to charges, Q1 plus potential due to Q2 plus potential due to Q3. Remember, potential is charge KQ over R. So total potential is going to be K, which is 8.99 times 10 power 9 times the first charge is positive 5. So that is plus times positive 5 times 10 power negative 6. The distance, we are still considering the midpoint. That will be 0.05 plus potential due to Q2 will be 8.99 times 10 power 9 times positive 6 times 10 power negative 6 divided by 0.05 plus potential due to negative 20, that will be 8.99 times 10 power 9 times negative 20 times 10 power negative 6 divided by 0.15. So I am going to press the calculator just once. For you can sum up each of these. Okay, I can sum up for you, no problem. Summing up this. This one is direct because the 5 cancels. So this is 8.99 positive times 10 power 5 volts plus, and this is positive. So this is plus 1.08 times 10 power 6, then plus the last one. This is most likely going to be minus because of this minus here. So this is minus 1.20 times 10 power 6. And when you press your calculator, so the calculator is giving me a positive 7.79 times 10 power 5 volts. Always realize or always note that an answer which is not exact should not be less than two significant figures in any paper of physics. Apart from the practical in paper 5, any answer which is not exact should always be written to at least two significant figures, at least. Okay, number 5. Number 5. A point A and B are 0.1 meters apart. A point charge of positive 3 times 10 power negative 6, negative 9 coulombs placed at A. A point charge negative 1 times 10 power negative 9 is placed at B. X is a point on a straight line through A and B, between A and B, where the electric potential is 0. Electric potential is 0. So there is a point between A and B where electric potential is 0. Now I want you to start noting that potential is 0 between two charges only if they are unlike charges. So one is positive 3 times 10 power negative 9. The other is negative 1 times 10 power negative 9. There is a point in between them where E is 0. I mean where V is 0. So at this point, the potential at the point P is 0. Remember, total potential is the sum of the potential due to each charges. And potential is given by KQ over R. So the total potential should be 0 at that point, and total potential is potential due to this charge, which is K times 3 times 10 power negative 6. This is positive, divided by the distance, which I'm going to call this distance X. And this distance will therefore be 0.1 minus X, because their separation is 0.1. So this one will be X plus K times, the other one is going to be negative 1 times 10 power negative 9 divided by 0.1 minus X. So you take 1 the other side because of this minus. So I will have that K times 1 times 10 power negative 9 over 0.1 minus X is equal to K times 3 times 10 power, this is negative 9, sorry, negative 9 divided by X. So power negative 9 has cancelled, K has cancelled. I'm cross multiplying 1 times X, that is X, 0.1 minus X times 3, that is 0.3 minus 3X. So when I rearrange, I'll have 4X being equal to 0.3. And when I press my calculator, X is 0.075 meters. So the distance AX, remember X was the point where E is 0. That's where I placed X is supposed to be the point where V is 0. So the distance AX is approximately 0.075 meters. Okay, example, I think example number 5, that is fine. The next example, maybe these could be the last examples. I've skipped several examples because they were a repetition. They were actually a repetition. How much work must be done by an external force in moving a charge of positive 2.0 microcoulombs from infinity to a point A 0.40 meters from a charge Q of positive 30 microcoulombs. So we are going to move a charge from infinity. No, we are moving a charge Q from infinity to that point. So we want the work done. So the work done to move the whole charge is going to be the charge times the change in potential, or times the potential. Of course, at infinity, potential is 0, so that one has no problem. So we simply substitute. The charge is 30 times 10 power negative 6 times, no, the charge is positive. Okay, let me just first rub off this so that people can understand this clearly. So potential so this will be charge times potential at a point, which is capital Q over times K over R, which is going to be positive 20 or 2.0 times 10 power negative 6 then times K, which is 8.99 times 10 power 9, then times the large charge creating the field, which is 30 times 10 power negative 6, divide by 0.40. Okay, I press my calculator to get the work done. So this gives me 1.35 joules as the work done. Number next. Two positive 30 microcoulomb charges are placed on a straight line 0.4 meters apart. A charge of a positive 0.5 microcoulomb charge is to be moved a distance of 0.1 along the line from a point midway between the charges. How much work must be done? Okay, so since I don't have enough space, I'll rub off this. I'll erase this. I use the same space. Maybe to understand this, I'll slightly sketch it. Let's say this is where we have positive 30 microcoulombs, and we have another positive 30 microcoulomb charge on that side. Then let's say this is the midpoint, that is the midpoint, and this was 0.4 meters, so this is 0.2 meters. This is also 0.2 meters. Let's say this is point A, the midpoint. And let's say the charge is moved 0.1, say from A to the other side. So this distance here is 0.1 meters. Let's say it is moved to point B. So once the work done, how much work must be done to move from A to B? So work done is going to be equal to charge times change in potential. The charge we are moving is plus 0.5 microcoulombs. All we need is the change in potential. To find the change in potential, remember potential is KQ over R. So we shall need potential at A and need potential at B. I'm very certain that potential at A is simply twice the potential due to one point. The potential at the midpoint is simply twice the potential due to one charge. So potential at point A is going to be twice 2 times K, which is 8.99 times 10 power 9 times 30 times 10 power negative 6 divide by the distance from positive 30 to A, which is 0.2. I've multiplied by 2 because I would get potential due to this plus potential due to that. Because A is the midpoint, I just multiply by 2. The magnitude is the same. So I press my calculator here. So this is 2.7 times 10 power 6 volts. That is the potential due to A. Then potential at point B will now be potential caused by this charge if we consider the distance, which will be 8.99 times 10 power 9 times 30 times 10 power negative 6 divided by 0.3, then plus potential caused by, I have said 0.3 because I'm considering the distance between this point and point B, then plus 8.99 times 10 power 9 times 30 times 10 power negative 6 divided by the distance which remains here is 0.1. I'll press the calculator once again. So this part is 8.99, or let me just write I will just write 8,99000 plus, because they are both positive, so potential is both positive. Then this one, this is 2.7 times 10 power 6. And when you sum up, the total potential here is 3.6 times 10 power 6 volts. So that is the total potential. Then change in potential or difference in potential is going to be the difference, that is 3.6 minus 2.7. So this is 0.9 times 10 power 6 volts. So the work done is going to be the charge, which is 0.5 times 10 power negative 6 times 0.9 times 10 power 6. When you press your calculator, you get 0.45 joules. So this must be the work done to move from A to B through a distance of 0.1 meters. Okay, maybe we can see some further examples. The graph below shows how the electric potential varies near a charged object. Calculate the electric field at a point C, 5 centimeters from the center of the object. So to answer this question, we begin by drawing the tangent at a point of 5 centimeters. At 5 centimeters, we draw a tangent. Then all we find is the gradient. Remember, I just mentioned the electric field strength is the negative potential gradient. We have in mind that the electric field strength is the negative potential gradient. So I will just draw the gradient at that point, and I try to find the gradient. I draw the tangent at that point at 5 centimeters. I try to find the tangent, the gradient of the tangent. So I am finding the gradient because I know E is equal to the negative potential gradient. So E is going to be equal to the negative of, so we have, I'm going to choose points here. We have 10.0 minus 2.0 divided by 0.6 minus 8.2. So this is giving me negative of negative um, negative of negative. Note that I've not converted. So negative of negative 1.05. This is kilovolts per centimeter. So if I convert, this will be negative 1.1 times 10 power 5 volts. I've just rounded off this to 1.1. So this will now be volts per meter. Note that electric field strength is the negative potential gradient. So that means, or when I multiply by the negative, this becomes positive. So the electric field strength is that value there. Okay, next. The electric intensity at the surface of the earth is about 1.2 times 10 power 2 volts and points towards the center of the earth. Assuming that the Earth is a sphere of that radius, find the charge held by the Earth's surface. So electric field intensity in our solution, E is equal to K Q over R squared. We just want Q. So Q will be equal to E R squared divided by K. If I substitute, E is 1.2 times 10 power 2, and R is 6.4 times 10 power 6, but this is squared, divided by K, which is 8.99 times 10 power 9. So this gives us 5.5 times 10 power 5 volts, coulombs. So the charge held by the Earth's surface is 5.5 times 10 power 5 coulombs. Lastly, last example, determine the work of an electric force which moves a point charge 4 microcoulombs from A to B. VA minus VB is 10, that is change in potential. That one is easy, I'll rub off this. So work done is equal to charge times change in potential. The charge is 4 times 10 power negative 6. The change in potential is 10, so this is just 4 times 10 power negative 5 joules. That's the work done. Find the electric potential in a vacuum at 0.2 meters from this charge. So this is the charge creating the field. We want the potential at this distance. Potential is equal to KQ over R. This is going to be 8.99 times 10 power 9, then times Q, which is 2 times 10 power negative 6, divided by 0.2. So this one reduces that, and this is going to be 8.99 times 10 power. So this is power 4. That would be power 4 volts. Okay, so finally we are almost done with the electric fields. All we need is to talk about something which may not be very important, but it's worth mentioning, and that is electric equipotential surfaces. Equipotential surfaces, what are equipotential surfaces? We talked about equipotential surfaces in gravitation, and an equipotential surface is any surface where all points are at the same potential. We have been seeing that work done is equal to charge times change in potential. That means if there is no change in potential, then the work done is most likely going to be zero. An equipotential surface is a point where, or these are points on the surface where all points are the same potentials. So we are going to see that the potential difference between any 2 points on that surface is going to be zero. That is, delta V is going to always be zero. And if that is true, then the work done to move a charge along this surface will still always be zero. That's what we are going to call an equipotential surface. We talked about equipotential surfaces in the gravitation, and we said they can be considered the same way we look at contours on maps could be the same way we look at equipotential surfaces. A simple analogy of equipotential surfaces can be seen in this slide. Let's consider a positively charged particle or spherical charge which is positive. Field lines originate from the charge and they radiate outwards. So if I could capture spherical slices around the charge, if I consider point A and point B, the potential at point A is the same as the potential at point B because potential due to a spherical charge is given by kq over r. If A is the same distance from the center as B, then the potential at A and potential at B are the same. And if that is true, the work done to move from point A to point B is going to be zero, since the change in potential is going to be zero. So if we have any 2 points at the same potential, we shall always conclude that the work done to move from one point to another point is always going to be zero, simply because the work done depends on the change in potential. So for an isolated point charge, all points equidistant from the charge are at the same potential. And it means equipotential surfaces in this case will be a series of concentric spheres with a point charge as shown. So these are going to be considered equipotential surfaces. This one, that one, that one. Those are different equipotential surfaces. You'll also realize that at any one point, the field lines are at, at a tangent to the surface, meaning that the force due to the field has no effect on the motion of the object along the surface. So the force due to the field or the electric field does not affect the motion or change the motion of the particle, of the charged particle along a given equipotential surface. For the force to have an effect, you must be moving either along the field at an angle to the field, or the field should be having a component along the direction of movement. But now we are seeing the charge is always moving at a tangent to the field, at a tangent to the field. So the force due to the field has no effect on the motion along the surface. So the potential will, however, be different if we have different spheres. It will always be different. If the charge is to be moved from any 2 points on the same equipotential surface through any path, the work done is always zero. When I move a charge from A, I move this side back to point B. Even if I take the same path from A to B, this other path from A to B, the work done will still be zero because there will be no change in potential, because any point along the same surface are at the same potential. So what I'm saying is that the work done is given by charge times change in potential. And if change in potential at A is the same as potential at B, then change in potential is zero. And we simply conclude that the work done is going to be zero. The work done is going to be zero. Equipotential surfaces can also we can also have equipotential surfaces on a uniform field. In the case of a uniform field, equipotential surfaces are parallel planes with their surfaces perpendicular to lines of force. So the electric field pattern of equipotential surfaces due to 2-point charges could also be shown here. So here I was showing you for parallel field lines where the field is uniform. We can take a small section through the field. At any point along this plane, the potential is actually going to be the same. So this plane will be standing for an equipotential surface. For 2-point charges, at any point along these field lines, at any point along this field line, the potential is going to be actually the same. At any point along this field line, the potential is going to be the same. So in general, we are saying an equipotential surface is a surface where all points are at the same potential, that moving a charge from one point to another point, there is actually no work done. In summary, I am saying the work done moving a charged body or a charged particle around an equipotential surface is always going to be zero, because the potential over the surface is a constant at any point on the same surface. Equipotential surfaces are always perpendicular. In other words, they make 90 degrees with the electric field. And two equipotential surfaces can never intersect. If two equipotential surfaces were to intersect, it would actually mean that it would be possible to have two values of electric potential, which in practice is actually not possible. It is actually not possible. So having seen all that, we can have a conclusion by looking at the graphs of electric field strength and um, potential against distance from the center. So let us consider a positively charged sphere whose radiuses are. We know that charge on a conductor resides just on the surface. We call that scientifically a Gaussian. Okay, charge on a conductor resides just on the surface. That means if we draw a Gaussian surface inside the sphere, it will enclose no charge. And by Gauss's law, electric field strength inside is going to be zero. But of course, we have seen that outside E varies as the inverse square of the distance from the center. Inside, because the charge resides just on the surface, it means inside the sphere, electric field strength is zero. Inside the sphere, electric field strength is zero. In fact, even charges are inside, even charges on the surface of the conductor could only move because there is an electric field just on the surface. But if there were charges inside the sphere, then they would actually not move because there would be no electric field inside the sphere. So we are saying, since the field strength is equal to the negative potential gradient, you therefore realize that electric potential inside the sphere is the same at all points and the same as that on the surface. We have established that E is equal to the negative potential gradient. A mathematician knows that when E is zero and yet E is the derivative of V, it means that V was actually constant. But of course, we have also noted that V varies as the inverse separation as you move out from the surface. So this is what we can generate when we try to sketch a graph. Look at one side of the sphere. If charges just reside on the surface, if I draw what I call a Gaussian surface inside the sphere, it encloses no charge. And if it encloses no charge, it means E inside the sphere is zero. E inside the sphere is zero. Actually, E, according to Gauss's law, would actually be equal to Q over epsilon or epsilon naught. But since Q is actually charge enclosed by the Gaussian surface. But because charge resides just on the surface, drawing a Gaussian surface inside the sphere means it encloses no charge. Therefore, E inside the sphere is zero. If I was to sketch a graph, inside the sphere, this will always be a horizontal line along the x-axis. But then at the surface, the value of E depends on the distance from the center. And as I move away from the surface, E reduces as the inverse square. Because E is the negative potential gradient, if E is zero inside, then V is constant and is the same as that on the surface. But as we move away from the surface, still V actually decreases. So the shape outside will be the same, but inside E will be zero, yet V is a constant. E would be zero, and yet E would be a constant. Okay, so that is about the graphs. And finally, we can look at a comparison and we conclude this. In comparison, at this point, you should have recognized the parallels. Those are the differences on your own. And here we have a useful summarizing activity, which is just a simple table. We have seen that for gravitational fields, the force between masses was always attractive. We have seen that for electric fields, the force can be attractive or repulsive because the field can be attractive or repulsive simply because we have both positive and negative charges. We have defined gravitational field strength as the force acting on a unit mass or the force per unit mass. And we have defined electric field strength as the force per unit positive charge. The units, these are obvious, newtons per kilogram or meters per second. And for electric fields, we have the newtons per coulomb and volts per meter. We notice that for a uniform gravitational field, we always have parallel gravitational field lines. Similarly, in electric fields, we shall also have parallel electric field lines. And G was always considered to be a constant close to the Earth's surface because we said close to the Earth's surface, since the field lines never cross, they are almost parallel to each other. And if they are almost parallel to each other, then the field can be considered to be uniform, so the field strength can be considered to be constant. On our next table, on our next slide, we are continuing the comparison. If we consider a spherical charge and a spherical mass, in both cases the field lines are radial. The field lines are radial. But note that if I consider a positively charged spherical mass, a positively charged spherical mass, yes, the field lines, the electric field lines will be outwards, but the gravitational field lines will be towards the charge. Because the gravitational field lines are due to the mass, yet the electric field lines are due to the charge. The field lines due to the charge will be radially outwards, yet the field lines due to the mass would be radially inwards because the gravitational force is always attractive. We saw that the force could be given by Newton's law of gravitation, and yet in an electric field the force was given by Coulomb's law. We derived the gravitational field strength as that because G was the force acting on a unit test mass. We also derived the electric field strength as that because E was the force acting on a unit positive charge. Note that the minus in gravitational field was indicating that the field was always attractive, but in electric fields, the field can be attractive or repulsive. So that was a further comparison. Maybe we can also compare in terms of graphs. So we have seen that the force and the field strength obey an inverse square law. I think we have seen that. The force and the field strength obey an inverse square law because the field strength G is inversely proportional to R squared. And also in electric fields, the field strength E was inversely proportional to R squared. But note, G was equal to capital negative G capital M over R squared. And I said, although in calculations this negative is ignored, the negative indicates that the force is always attractive. Attractive forces are assigned negative values, therefore giving us a negative gravitational field strength. In electric fields, we can have a positive charge giving a repulsive force which is positive, giving us a positive electric field, and a negative charge which is attractive, causing a negative force because attractive forces are negative, which will give us a graph below the x-axis. That's why we are seeing that E due to a positive charge is above and E due to a negative charge is below. These graphs are starting just on the surface, just on the surface, just on the surface. Remember, E inside, if it was a spherical conductor, we have already seen that E inside would be 0, which would be a horizontal line along the x-axis. We also looked at potential. Where we said gravitational potential is negative capital Gm over R. That is, it obeys an inverse relationship, and it was 0 at infinity. Similarly, electric potential is 0 at infinity, and V is inversely proportional to R. So you notice that in both cases, the potentials follow an inverse relationship, not square. If we look at the graphs for potential, since potential is always negative, gravitational potential is always negative, the graph will be below the x-axis. Note that this is also from the surface, because inside we may not be interested in what is happening inside the mass right now. In a similar way, potential can be positive if the charge is positive, potential can be negative if the charge is negative. Okay, so in conclusion, you must have observed the following. Number one, a few similarities that you have observed include the following. The field strength due to a point charge or mass, or in other words, the field strengths and the force due to these fields follow an inverse square law. Force is inversely proportional to the square of the separation for both fields. Strength or field strength, I don't want to use any letter for strength because there are two letters, G for gravitational and E for field, electric field. But strength also follows an inverse square law. G for gravitation is capital G m over r squared, and E for electric fields is kq over r squared. Number two, you must have seen that in both cases, potential and potential energy are inversely proportional to distance. We saw for gravitation, potential was equal to negative capital G m over r, and we have seen that for electric, potential is equal to kq over r. In both cases, potential is inversely proportional to the separation or distance. Number three, we have defined the zero of potential to be at infinity for both fields. For spherical bodies, if it is a mass, the field lines are radially inwards, and if it is a charge, the field lines are radially outwards. So, for spherical bodies, the charge or mass on the sphere behaves as a point charge or mass at its center. Why? We have seen that since the field lines are radial, they appear to be terminating to the center if it is a mass, or to be radiating from the center if it is a positive charge. So spherical masses and spherical charges can also be considered point charges since the field lines are radial and appear to be originating from the center. You must have noted the major difference. You must have noted this major difference or these major differences. Electric charges can be positive or negative. What does that imply? It implies that electric fields can attract or repel. We do not have any negative masses. Therefore, there is only attraction in gravitation fields. So the force due to gravity is only attractive, is always attractive. The force due to electric fields can be attractive or repulsive. The force due to electric fields can be attractive or repulsive. There is only attraction in a gravitational field. One major difference between the field lines is that the field lines due to masses are radially inwards, yet the field lines with electric fields can be radially outwards or radially inwards depending on the sign of the charge. I'm talking about spherical charges and spherical bodies. Gravitational potential was always negative. Reason: potential at infinity is zero, and yet the force between two masses was always attractive. Work is always got out when you move a unit mass from infinity to a point in an electric field. Whereas electric potential can be positive or negative depending on the sign of the charge. Maybe to sum up this, before we see a past paper question, I want to help people, before we summarize this, I want to help people to be able to distinguish between like charges and unlike charges using a graph. Suppose you are given a graph, will you be able to identify that the charges for which the graph is drawn are like charges or unlike charges? Let us see. So we are going to consider, sorry, we are going to consider two charges. Let's say they are like charges to begin with. Let's say we have two positively charged particles. Okay? If I know that these are two positively charged particles, we know that like charges repel. And if that is true, suppose I consider a distance x, which is measured from charge A as we move towards B. If I consider electric field strength, I always imagine a unit positive charge at a point somewhere so that I can tell the direction of the field. Charge A repels this to the right, charge B repels this to the left. What does that mean? There is a point between A and B where the field strength becomes zero. So if A and B are perfectly identical in magnitude, then the point where E becomes zero must be right at the center. So if I was to sketch a graph, let me try to sketch a graph. If I was to sketch a graph of electric field strength with the distance from the centers. So here I have charge A, spherical charge B, spherical charge. This is A, that is B. I'm trying to sketch a graph of electric field strength with the distance x from the center. I mean from the surfaces. Even if I include the center of these spherical charges. I know, or you must have noted, that E inside the conductor is always zero. So if these are identical conductors, or I've drawn them wrongly, inside the conductor, the line for the graph will be along the x-axis. But on the surface, we have seen that E is equal to kq over r squared. So there will be a value for E just on the surface, which is depending on the radius of these spheres. But when I move from sphere A to sphere B, there is a point somewhere at the midpoint where E becomes zero. If they are identical spheres, this point will be exactly at the center. So as x increases from this surface, the other surface, E reduces and it becomes zero at that point. And it has started from a certain magnitude on surface. If these are identical, then E changes direction. As I move towards B, E increases, but in the opposite direction. When you are closer to this point, the repulsion caused by this charge is greater than the repulsion caused by this one, so E is to the right. When I come closer to B, the repulsion caused by B is greater than the repulsion caused by A, so E is to the left. So E changes direction, therefore the graph will be below the x-axis. But the magnitude is going to be the same as this magnitude here will be the same as that magnitude on the surface if the two charges are identical. So how do I tell that the two charges given are identical from the graph? When the graph crosses the x-axis, it means there is a point between the two charges where E becomes zero. At that point, F is zero, and that point is called a neutral point. There is a neutral point between two charges, and earlier on we saw that the neutral point only exists in like charges. So the same thing would happen with the negative charges. But if I find potential for the same two positive charges, surprisingly, if I find potential, because potential is equal to kq over r, and the potential depends on the signs of the charge. If both charges are positive, the total potential is still positive. So if I draw a graph of potential with the distance from the surfaces, this is the surface of charge A, this is the surface of charge B. This is the surface of charge B. I need to make this one a little bit clearer. So I have the surface of charge B there. Note that if these are like charges, inside the conductor potential is the same as just on the surface and is constant. So we have a horizontal line there inside the conductor. And because this is positive and this is positive, for both potential is positive, maximum potential will be the same. So we shall also do a horizontal line here. But as I move far from charge A, closer towards charge B, the potential decreases Potential is high when I'm very close to this charge. It decreases to a minimum value midway between the two charges. Now it starts increasing, but it is still positive. So the potential will be, the graph for potential will have a minimum at the midpoint. So it will have a minimum point here. It will not be zero, it may not be zero. But what is very important is that for both positive charges, the potential is positive. If both were negative charges, then the potential for both for both charges will be below the x-axis. It will be just the mirror image of this. So this will be the graph of potential with the distance from one surface to another surface. If we have like charges now, if I have positive and negative, then for electric field strength, it will always be towards the negative. If this is A and that is B, moving a distance x from the surface towards B. If I imagine a unit positive charge placed somewhere here, this charge which is negative will always attract it to the right. The positive charge will always repel it to the right. So at any distance between A and B, between the surface of A and B, E is always in one direction. So it means if I have a graph of E with the distance, a graph of E with the distance, if I have a graph of E with the distance, then this graph will never change, will never cross the x-axis, because E will always be in one direction if I have unlike charges. In fact, E will always be towards the negative charge. Therefore, the graph for this, there are two spheres or two charged spheres, where that is the center of one, that is the, okay, let me draw something better. So if I have two charged spheres, let this be the surface and this be another surface. So let this be the the y-axis, and then the x-axis between them. So this is the surface of one sphere, spherical charge, and this is the surface of another spherical charge A. We are trying to sketch E. Note that E inside is zero, because charge on a conductor resides just on the surface. Charge on a conductor resides just on the surface, so E inside is going to be zero. E inside will be zero. Because this is positive, the other one is negative. As I move from the surface to the other side, what happens to E? E is stronger when I'm close to A, and when because E is depending on the distance from this, but E does not change any direction. As I get to the center, E may reduce, but then it again increases as I get to the other next charge. So this will be a graph looking like this. It will be minimum at the center, and then it increases to the maximum when you get towards the negative charge. So the graph would be like this. E on the surface is a certain value which decreases to a minimum as you move towards the center, but does not cross the x-axis because it doesn't change. E does not change direction because it is always in one direction. So that is for like unlike charges. But if it was a graph of potential, then the reverse is very true. If it was a graph of potential, then potential would cross the x-axis. Potential would cross the x-axis. This was E against the distance. The graph of potential would cross the x-axis. Remember, when E is zero, potential is a certain value. Potential is a certain value. When, of course, as you move away from the surface, potential decreases. So you'll have a graph going to zero. And Because potential due to a positive charge is positive and potential due to a negative charge is negative, if the two are equal in magnitude, then the potential becomes zero. So here potential becomes zero. And then here we can't say potential changes direction because potential is a scalar quantity. Or we can say that potential becomes negative when you move towards the other surface. But if the charges are identical, the magnitude will still be the same. So on the inside, remember its potential is constant, where E becomes zero. We shall understand these graphs in details in the past paper questions. So for now, I thank you for watching this video. I am going to upload it and attach past paper question documents for some of you who may not be having it, and always refer to it when you are watching the next parts or the next episodes of solved past paper questions in electric fields. I hope you have enjoyed this. I hope it has been useful, and have a good day. Bye bye.